Hello, in this lecture we are going to discuss one more data structure, which is backing few collections classes in Java. At the beginning of this chapter I promised that I will leave no doubt how everything is working internally, and to be able to fulfill that promise we have to take a look at the tree data structure. A tree is a data structure which is used for storing hierarchically ordered data. If you take a look at the diagram, it looks like a reversed tree. Tree's elements are called nodes. Each node has two parts, data and links to other nodes. There are a lot of different types of tree data structures. We are going to discuss just the ones that we will need for this course. The tree is the abstract data structure. We need more concrete implementations with some restrictions to be able to create well-performing collections. But before we go to that, let's see some of the tree terminology. Root is the topmost node of the hierarchy, or it is the node from where the tree starts. In our example, 1 is the root, because as you see, everything starts from it. Next we have child. Nodes next in the hierarchy are children of the previous node. For example, 2 and 3 and 4 are children of 1. 5 is a child of 2. Next we have a parent. The node previous to the current node is parent of the current node. For example, 4 is a parent of 6, 7 and 8. 8 is a parent of 9. So a node can be simultaneously a child and a parent. 2, 4 and 8 are examples of that. Then we have siblings. Siblings are nodes having the same parent. In our example, 2, 3 and 4 are siblings. Also 6, 7 and 8. Level is the level of depth or height of the tree, depending on the point of view. Leaves are nodes that have no children. In our examples, 3, 5 and 9 are leaves. The depth of a node is the number of nodes on the path from the root node. For example, 2, 3 and 4 have a depth of 1. Then 5, 6, 7 and 8 have a depth of 2. 9 have a depth of 3. Height. The height of a node is the number of nodes on the longest path from the node to a leaf. For example, 4 has a height of 2 and 6 has a height of 0, as 6 is a leaf. As you can see, some of the terminology is relative, depending on where we are at the tree. I hope this is clear so far. Let's continue. We will take a look at the first more concrete implementation of a tree. Binary tree. A binary tree is a tree in which each node has 0, 1 or 2 children. Binary trees are probably the most used ones, but again, they are kinda abstract, either though they have some restrictions. Two types of binary tree are full binary tree, which is a binary tree in which every node has 2 children except the leaves. So if you look at the tree we have here, this is not a full binary tree. What do you think? What do you think it should happen so we can transform it to a full binary tree? The quickest solution here would be to remove the node with number 8. That will leave us with a full binary tree. Now all the nodes except the leaves has 2 children. Next we have a complete binary tree. A binary tree which is completely filled, with a possible exception at the bottom level, meaning that the last level may not be completely filled, and the bottom level is filled from left to right. So in our case we have a full binary tree, but it's not a complete one. To do that, we can either remove the last 2 nodes on level 3, which are the ones with numbers 6 and 7, or we can add 2 nodes below node 3, which will lead to a bit of reordering. Now we have a complete binary tree, and for that fact this is also a full binary tree. So we have a complete and full binary tree. Complete binary tree has some useful properties. First, the parent of node x is floor function of x divided by 2, except the root node, which has no parent. For example, the parent of the node 2 is 2 divided by 2, so 1, and the parent of node 3 is also node 1, which is again a floor function of 3 divided by 2. Second, the left child of node x is 2x, if the left child exists. For example, the left child of node 3 is 2 multiplied by 3, or node 6. And third and finally, the right child of node x is 2x plus 1, if the right child exists. For example, the right child of node 4 is 2 multiplied by 4 plus 1, so node 9. Let me go a bit deeper and explain how binary trees are living in the memory. We can go two ways, using arrays or using linked list. We will concentrate on the array representation. A binary tree can be stored in a single array. We give numbers of the nodes from top to bottom, and for nodes on the same level from left to right. The values of the nodes are stored in an array with the index corresponding to the numbers given to the nodes. Let me elaborate on that. Take a look at the binary tree which is currently being displayed. We store some letters values in the nodes. Above, we have the corresponding index in the array. Please look below to see how would the array representation of the tree look like in the memory. The array is filled from index 1, and the element at index 0 is left empty or null based on the data type. So now we have an empty space in 0, then we have h on index 1, y on index 2, g on index 3, etc. For an incomplete binary tree, we first assume that there are nodes present to make the tree a complete one, and then fill the array's proper positions. So if you take a look at our binary tree, it's been changed, and the solid nodes are the ones which we have left. But to represent it in the memory, we should imagine that we have old nodes, like a complete binary tree. So the array would look like this now, with empty spaces on the indices where we have no nodes. Now I promised I will not explain deeply the linked implementation, but here is how it would look like. In the linked representation, the nodes contain mainly three elements: the data to store, a link to the left child, a link to the right child. That's it. So they are using pointers, just like a regular linked list, which I've explained already. Okay, and finally, the data structure which is important for our next lesson: heap. A heap is a data structure that uses a binary tree for its implementation. It is a complete binary tree which is array represented. Heap is used to implement priority queue class. Now you know why we went through all this. There are two kinds of heaps. Max heap. In a max heap, the value of a node is greater than or equal to the value of its children. And min heap. In a min heap, the value of a node is either smaller than or equal to the value of its children. In the maxed heap, the largest element is at the root. In a min heap, the smallest element is at the root. When an element is inserted or deleted from the heap, if there is any violations of the heap constraints, the heap is resorting itself to satisfy the constraints. This is done behind the curtains, and the time complexity of this algorithm will be logarithmic. So, as you can guess, what we have on the diagram is a max heap. What is important here is that every parent node is greater than its children and smaller than its parent. A min heap would look like this, having the smallest element in the root. Well, okay, that was it. That was all about trees for now. In the next video, we will see the collection which is being backed by Heap, priority queue. See you in the next video.
For more details, check the link in the description. Learn with Whizlabs. Success certified.